Okay, today we're going to be starting our next stuff, and it is about sound waves. Say what? So the first thing we need to talk about is what they look like. Sound waves are longitudinal waves, okay? Now normally when you think of waves, you think of waves like this. Now sound waves don't actually look like that. Sound waves don't have vibrations that go up and down. Sound waves have vibrations that go back and forth in reference to their traveling. So what that means is, let's start with an example here. Here's a drum. If you hit the drum with a mallet, what's going to happen is the drum is going to bend in the film, the skin on the drum. And then it's going to bounce outwards again. So it's going to bounce between these two positions. Now this will compress the air, and then it will bounce back and it will expand the air. So there will be basically wave after wave of compression. All right, and that's what sound is. Sound is. Now it's called a longitudinal wave because if I were an air molecule, what would happen is when the wave hits me, I'm going to move this way and then that way, back and forth, right? So I'm going to get pulled towards one wave and then I'm going to be done with it. Now it's called longitudinal because it's vibrating that way and the wave is traveling this way. For this type of wave here, it's vibrating up and down, but the wave's traveling this way. These are perpendicular and these are parallel. That's why it's called a longitudinal wave. All right? So that is what the sound waves will look like. Now, obviously, when we draw them, we are going to draw them like this. But what this is really representing is this is representing the amount of compression. Okay? So, for example, right here, there is no compression. Well, less compression, negative compression. So it's going to be there. If I put a point Y right there, that is going to be on the high point in the previous wave. So it's just like if we graph this, how much darker it is, how many lines there are. If there's more lines, it would go higher. All right, so we're going to look at the details here. The first thing we're going to talk about is pitch. Pitch is how high or low the sound waves are. Okay, so this is going to depend on the frequency. Alright, so the frequency is how many waves per second. Okay, so let's give you an example. Here's a wave like that, and here's another wave. Okay. Now, let's say they're moving forward at the same rate because it makes it easier. If this is 1 second in time here, right? This wave goes up and down once, up and down twice, up and down. Well, almost up and down and back. So this has a frequency of 2.5 waves per second. All right? This one goes up and down much more times. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this has a frequency of 10. There's 10 waves per second. Now, waves per second has a simplification. It is a hertz. So this is going to be 2.5 hertz, and this is going to be 10 hertz. Now, human hearing is about 20 to 16,000 hertz. So your very low notes are going to be on the lower side. So this is a low pitch. This is a bass sound because it's all about the bass. Whereas this is a high pitch because it goes back and forth faster. It has higher frequency, higher pitch. It's more Mickey Mouse style. Nothing but treble. Okay, so you can hear between these ones. Now, obviously, when you're older, this amount changes. As you grow up, as you listen to what you call music very loudly in your headphones, that will decrease the range. Old people can't hear the high pitch as well, especially, which causes them to have more hearing problems. That's why they can't understand you. They can't hear the higher parts of your voice as well, or at all. Okay, let's talk about the next thing. The next thing is loudness. What? So loudness depends on the amplitude of the wave. What is amplitude talking about? How big the waves are. Okay, so let's draw, two situations here. Here's a wave, and there's a wave. So these waves have roughly the same frequency, right? They both have 1, 2, 3. They both have a frequency of 3 hertz, but they have way different amplitudes. If we draw a line down the middle, this one has an amplitude of this much, whereas this one has an amplitude that's way bigger. Now, this wave here is going to have more energy, right? Think about your drum, right? If you have the drum bend back further, it's going to have more energy. It's going to make a louder sound. Now, these are the same pitch, but one is louder than the other. Okay, this one is louder because it has more energy to it. Now, loudness is measured in a couple different things, but usually absolute loudness is measured in pascals. Remember how this creates pressure waves, right? Pressure waves, pressure is measured in pascals, which is a force per area. Right? Hopefully you remember that from recently. Now, absolute loudness is measured in pascals. This is your average human range for loudness. Now, this isn't practical because we'll talk about why in a second. But you can hear from between, this small amount, which is in 2 10,000ths of Pascal to 20 pascals, which would be very, very loud. Not necessarily healthy, but you could probably hear it. And of course, this does vary a little bit from person to person. Let's talk about a more useful way to measure loudness, and that is in decibels. Now, decibels is a comparison measurement, all right? So basically, it compares loudness to something. All right. Now, it is a comparison measurement, and we also need to say that it is logarithmic. Let's see, I-T-H-M-I-C. I think that's how you spell it. Anyways, don't worry about that. Let's talk about logarithmic first, because it'll help us understand comparison measurement. Let's talk about what's not logarithmic. Let's talk about a linear measurement. Okay, let's say I've got loudness, linear is a straight line, right? So this is loudness A, and then if I times it by 2, I get loudness B, and loudness B is going to be twice as much, give or take, right? This is a linear measurement. Logarithmic doesn't work that way. A logarithmic graph will look something like that. Okay? So here's loudness A, and here's loudness B. If I times 2, it's not going to be twice as much. It's going to be less than that or whatever. Okay? So here's how, this factor will change depending on the graph. I can make it flatter, I can make it taller, but we'll talk about that in a second here. So here's the formula for decibels. A decibel is abbreviated dB because this is one of your metric prefixes, is going to equal the log, it's going to equal 10 times the log, 10 because of the deci, of a fraction. A fraction is going to be your pressure divided by your pressure 0. Now, this is the pressure of what you're hearing, right? Whatever sound you're talking about. This is the lowest measured pressure for hearing. Lowest measured pressure. So maybe you remember before we talked about the lowest amount you can hear. This is that lowest amount. So this amount was the 0.000002 pascals. So your big hearing is going to be just whatever ratio it is above that. Now the logarithmic means that when you go up by pascal or decibels, right? It doesn't go up at the same rate because it's not linear. So if you have 10 decibels, right? Let's pretend that's something you heard. And then it goes up to 20 decibels, all right? It's not twice as loud. It is going to be times 10 as loud. Every time you go up by 10, this number here, it's times 10 as much pressure. Okay, and then you can break that down in a second here, but let's talk about just a scale so you get an idea. So here are some decibels of things that you might have heard before. So decibels at 10 is barely audible. You can barely hear something. Now, it's not the lowest. The lowest you can hear is actually 0 decibels. Okay, how does that work? Well, because it's math. There is a 0 for this. And that's the smallest possible hearable thing. Now, if you go from 10 up to 30, you are going to increase the amount of pressure, increase the amount of energy by 100. Okay? Now, the reason is because if you go 10 up to 20, that's times 10, 20 up to 30, and that is times 10. So if you go times 10 twice, you are going to go times 100, because 10 times 10 is 100. All right? So if you have 100 people that are barely audible, that adds up to a whisper. If you have 100 people that are whispering, that is just as loud as talking. And these are all rough estimates, right? Just to give you an idea. Now, talking goes to traffic AM. This one is going to be times 1,000 because you're going up by 30 this time. So 3 times 10. And so on and so forth. So here you have rock concert going to discomfort, discomfort changing to pain, and then at the very end, what you have are the school assemblies at 9,000. Okay. So these are some decibels, so you need to know how the decibel system works, generally speaking. You're not going to have to calculate this over and over again, but you just need to know what you're actually measuring by. So if it goes up by 10, what that means is you're timesing it by 10. You're not just going up a little bit. Each increase is huge. All right, so we're going to do some practice with this, but we are actually going to combine it with tomorrow's practice, so we'll see you then.